in the news feed, I tell everybody about that they can move their test from to the 29th or the 30th of May if we have to. So, but anyway, hopefully my pen's working now. It didn't work before, but it's working now, so that's great. So as I was trying to say, this unit, sections 1.4 and 1.5 are all about quadratic equations or quadratic functions. And the idea is that when you graph a quadratic, and quadratics are always in the form of ax squared plus bx plus c is equal to 0. Or if you're going to write it in function notation, they look like this. And it's a polynomial, which means that we have more than one term. And the highest degree is going to be a second order polynomial because the highest power we have is 2. And you have to have x to the power of 2 in order to be considered a quadratic equation. So that's how it kind of opens section 1.4, is being able to identify whether you have a quadratic equation or a quadratic function or not. And it's going to be this x squared, because you can just have y equals x squared. That is a quadratic equation, even though you don't have a b or a c value. You can still, this would be like the smallest requirement is that you have this x squared. And when you graph that, you get this nice horseshoe graph called a parabola. And all quadratics will draw a parabola, either right side up, or it could also be upside down. But never sideways. You won't get a quadratic that will give you a parabola that goes sideways. That's a different type of function, but either a parabola that opens up or a parabola that opens down. And the reason why we are looking for the zeros of the function, the zeros are looking for what x is equal to when y is equal to 0. And on a graph, when y equals 0, we're looking at the x-intercepts. So for just your function of y equals x2, your x-intercept is going to be at 0 and 0. So x is equal to 0 for that. If you have a quadratic that does not pass through the x-axis like this, then you're not going to have any zeros. You're not going to have any x values because we don't have any x-intercepts. But section 1.4 and 1.5 is all about finding zeros, because that's one of the easiest ways to find to graph a quadratic, is to solve for the zeros, because that's going to give you 2 points or 1 point where the graph is going to pass through the x-axis, and then the other point that will help you to graph is going to be the vertex, and the vertex is always either the minimum or the maximum value on a parabola. So your minimum is going to be the bottommost point if your graph opens up, and your maximum is going to be the topmost point. And these minimum and maximum are called the vertex. And we're going to learn in section 3.1 how to find the vertex. But first of all, we need to find our x-intercepts, or the zeros of the function. So that's why in 1.4 and 1.5 we're looking at a bunch of different equations and a bunch of different strategies in terms of how to solve for these zeros, and which strategy you use depends on what form your equation is in. And the first thing that they look at is factoring. So we're bringing back, I think it's unit from Math 1046, when you're factoring polynomials, we're bringing back that part. So the first part of section 1.4 is just reviewing how to factor a quadratic. And I believe in the video that I sent out for 1.4, I go over the method that I like to use, which is the X method, or the British method, where you find a times c in the quadratic, that's a c, and then put b below, and then find out all of the factors when multiplied together give you this top number, and when added together give you the bottom number, and then you can use those two factors to help you to factor the quadratic. But before I get into that, I wanted to show you the question that was sent to me. So I'm just going to get rid of this here. So if you have a quadratic that's not that you can't factor easy or is not factorable, the other thing you can do is use the quadratic formula. And the quadratic formula is a formula that will give you your x values or your x-intercepts for an equation. And it's always in the form of negative b plus or minus b squared minus 4ac all over 2a. And this quadratic formula will solve for x for any quadratic that you throw at it. So if you have a quadratic that is easily factorable, but you don't want to factor it, you can use the quadratic formula. If you have a quadratic formula that's missing a b value or an a value, you can still use the quadratic formula. You're just going to put zeros in for that. It will solve any equation that you throw at it, and a lot of students will find that they will use the quadratic formula even though it's not the easiest one to use, just because they know that in the end they're going to get the correct answer. So that's why most people really like the quadratic formula. But one thing about the quadratic formula, and I'm just getting my notes here, it can also predict whether you're going to have x-intercepts or not, because, as I said before, when you draw a parabola, if the parabola intersects the x-axis, that's going to be your zeros. But not all parabolas intersect the x-axis at 2 points. For instance, y equals x squared only has one x-intercept at the origin. And then some parabolas don't even go through the x-axis, and therefore you're not going to have any zeros. And it's going to be the quadratic formula that can tell you whether you have solutions or not. And so I'm just going to go over that. What you're going to do is you're going to determine, you're going to find the discriminant. And the discriminant is this part of the quadratic formula here. Let me grab a different color. So just b squared minus 4ac, that's called the discriminant. Have you gotten this far in the in section 1.4 yet, Andrew?
Yeah, I have.
Oh, good.
I watched both of the videos, so I took some notes on the discriminants and
Great.
the zero, the negative, or the positive, and what they look like.
Awesome. So do you find that you watch the reviews before you even get started, or do you do some work and then watch the reviews? How do you use the reviews?
I watch reviews first,
Cool.
and then I go back and usually watch it a second time and take notes. And then I get into my math lab, and then usually I get about 10 questions done, and then I have to go back to the video.
No, that's great. I really like that of using the review first. That's a great strategy, and I know students that use it at the end as just to kind of bring everything together. So whatever works for you is great. I find it interesting to see how different students use it. So that's really cool.
Yeah, just for me personally, I just find that I have less frustration with the math lab stuff if I have a little bit more knowledge going in.
Yeah, a little bit of a heads up, right? Well, if you've already been here, so basically when you go to graph something, if you want to see if it's going to pass through the x-axis and how many times it passes through, for instance, if you're going to have one solution, two solutions, or no solution, it's all about the discriminant. So what you can do is kind of piece out the discriminant, and if the discriminant is positive, which means that it's greater than 0, then you're going to get two solutions. If the discriminant is equal to 0, that means you're only going to have one solution, which means that either the maximum or the minimum value falls right on the x-axis. So the vertex is going to fall on the x-axis if the discriminant is equal to 0. And if the discriminant is less than 0, so a negative number, that's going to be that situation where you have no solution because you have a floating, what I call a floating parabola. So it's not going to pass the x-axis at all, and that's going to be when the discriminant is a negative number. And the question that was asked for me today is based on that type of a quadratic. What happens if you have a quadratic where the discriminant is equal to a negative number? Can you solve for it? And you can, but the solution you get is an imaginary 0, so they don't actually exist, but you can still reduce the answer down to an imaginary number. So I'm going to give the example. It was in my math lab. I'm going to change my pen over, and they gave the quadratic formula as this, -6. So they didn't give the quadratic function. They just went ahead and gave the formula.
This is question 12, isn't it?
Let me see.
This looks like the one that I had the question about.
Oh,
so this
awesome.
is good.
This is good. It is, I'm just bringing it, I don't have the question number, but it says it's 1.4 CV, which is the concept vocabulary check, number 12. So that's what came through to me through Ask My Instructor, but that's the one. So if you see that indication at the top, then it's the same one. And the question says simplify this quadratic formula. And it does give you a negative underneath the radical sign, which means this. The discriminant is negative, so you don't actually have any solutions. It's an imaginary solution. And then underneath, it's 2 times 3. So the question was, how do I reduce this into a final answer correctly? So that's what we're going to work through. So I like to take it piece by piece and work on simplifying it as I go. So right away, I can simplify the denominator of 2 times 3. That's going to be 6, so that's pretty easy. The -6 I just have to leave. And then I'm going to try and simplify under the radical sign. So I have 6 to the power of 2 is going to be 36. And then -4 times +3 times 4 gives me -48. I will say that most students, when they are doing the quadratic formula and the discriminant, if there is an error, it's usually in this part of the discriminant because they forget to include the negative when they're multiplying, and their answer for this part here, they get the sign wrong and that messes everything up. But it is -4 times 3 times 4, which does give us -48. And then I'm going to do another line, and I get -6 plus or minus the square root, and now I can do 36 minus 48 gives me -12 all over 6. Now students get to this point, and it's that age-old problem of, have I simplified enough? And the answer to this is that you're close, but not quite simplified enough. For instance, if you look at the you have -6 over +6, so at least that side can be reduced, but we also don't ever like to see a negative under a radical sign, under the square root sign. So I'm going to show how you simplify the -12 into its most simplified form. And again, this -12 tells us that we're going to have a floating parabola that doesn't have any x-intercept. So whatever answer I'm going to get here for what x is equal to, it's going to be an imaginary number. It's going to be an imaginary 0 and not actually exist, but we still mathematically want to have this in the most reduced form. So to do that, what I'm going to do is I'm going to expand that square root of negative 12. And I'm going to expand it into its factors. So negative 12, I'm going to parse out the negative 1 because I'm going to turn that into the complex number of imaginary I, and that comes back from when we worked with complex numbers in Math 1046. So I'll remind everybody about how to get rid of that negative 1. And then I'm going to times that by 4 and times that by 3 because that's the factors for negative 12. So negative 12 can be reduced to negative 1 times negative 4 times, negative 1 times positive 4 times 3 gives me negative 12. Andrew, do you follow that, how I got from negative 12 to this?
Yeah, I sure do, and I
Okay.
even think I know the next step.
Oh, good. What's the next step?
Well, you're gonna pull out your I,
Yes. So,
and
yeah.
you're gonna make that into
Oh,
2 root 3.
yeah, that's it. I'm going to just do one extra step just for students that might not make that leap, but I can basically take the square root of negative 1 times 4 times 3 and just pull them all out separately like this. And then what I can do is I can simplify. The square root of negative 1 is always going to be I. So that's what you said, take out the I. So I can take out that. The square root of 4 is 2. That's the square root of 4. And square root of 3, it's not going to be a whole number, so we're just going to leave it as that. So when I rewrite this, I'll have negative 6 plus or minus 2i, because that's the proper way. You never want to say I2. 2i is the proper way to write that. Square root of 3 all over 6. Does that look okay, Andrew?
Yeah, so far.
Yep, so far. So it looks like I'm almost got it down simplified. The biggest thing here was, as I said, going from square root of negative 12 to 2i square root 3. That's a big leap, and again, this is something that we did in Math 1046, so it's kind of nice because now you get to kind of practice that skill again, but that's where this comes from. And then what I can do is I can simplify. Again, I'm going to take this negative 6 here, and that's over 6. So negative 6 over positive 6 plus or minus 2i square root 3 also over 6. So I just parsed this expression into 2, and the reason why I wanted to do that is I can now reduce this fraction of negative 6 over 6 to be negative 1 plus or minus, and I can also cancel out these. 2 goes into both 2 and 6, so 2 goes into 2, 1, which I don't have to write down, and 2 goes into 6, 3. So there's my final answer. So to reduce the two fractions, I just separate that main expression here into two separate expressions with a denominator of 6, and then I canceled out where I could. Negative 6 over 6 is negative 1, and 2 over 6 can be reduced to 1/3, and I took out the 1 here because you can take that out, and I'm left with I times the square root of 3 over 3, and that's as far as I can go. That's completely simplified. But that's what the student was asking. They had gotten to, I believe, this part here, or pretty close to it, but it was getting it into this 2i square root of 3, and then dealing with the fact that we were still able to reduce the fractions within that expression. But again, this is a completely imaginary number that and is telling us that we don't actually have x-intercepts for this parabola, but in math, even though it's imaginary, we still like to be able to bring it to simplest terms to work with. Andrew, any questions about that?
Yeah, you know, okay, so you have here your plus minus. Um,
Yes.
do they want you, because I think in math lab sometimes when you have that plus minus situation, they want you to give two answers.
Yeah.
They
Yes.
want you to give the negative one um, imaginary number root 3 over 3, and then they want you to give negative 1 imaginary number 3 over 3,
Yes.
root 3 over 3.
Yeah, like that. So if they don't, I can't remember, there might not be a plus minus in the little tool bar at the bottom. And if it's not there, then that means
There
you're going,
is.
oh, is there? Okay.
Yeah, yeah.
But if you wanted to write out the two x values, then you would write the expression out with just the positive, and then you'd write it again just with the negative. And I think this one might have had that. Let me see. Sometimes you can write both with just separating a comma between them as well.
Yeah, I don't think
This one
that's how
was a
they wanted
comma.
it. Yeah. Oh, was it? Okay.
Yeah,
Yeah.
yeah. But that's it. So that's using the quadratic formula. Even when your discriminant comes out to be a negative value, you can still work through it, take out your imaginary I number, and then try and get it to simplified terms. Now, if you did this on a test and you got to this point here and didn't simplify it all the way, I would give you 0.75 of a mark out of 1 for that. So just remember that if you don't get it to simplest terms but you have the right answer, that's something that you'd want to email me after your test and say, look, Laura, can you look at question number 4? I have the right answer, I just didn't simplify it all the way, and I'll be happy to give extra marks for that. And that happens. That happens sometimes. So that's it. That's
All
the
the
only one that
time.
was emailed to. Yeah, all the time. That's the one that was that was the only one I received through email. Andrew, I'm going to take this off if you're okay with that. And then you said that you had, this was one of your questions, so we killed two birds with one stone with this one, so that's great.
Yeah, I also feel good that I'm not the only one who had issues with it.
Exactly. That's always like, oh good, I'm not the only one. So
Exactly.
what do you have another one for me?
Mine would have been question 26. I have it here if you just want me to read it off to you.
Sure, I can try and do that, but if not, I'll go into my math lab. But yeah, let me know what it says.
It's 3x squared
3x squared
minus 9x
minus 9x.
minus 6
Okay.
equals 0.
Yeah.
And they want you to, what do they want you to do? Shoot. They want you to complete the square
Oh, okay.
to solve this problem.
Okay. So when you're cool. So to complete the square, the idea is that we're going to add b divided by 2 all squared to both sides to make a perfect square trinomial. And the reason why you want that perfect square trinomial is that it will it will make your quadratic factorable, which is nice. Right now, this quadratic I don't think is factorable. Let me just check. So if I do the British method and I times my a value by my c value, I get 3 times negative 6, which is going to give me negative 18, and my b value is negative 9. So I'm looking for two numbers when multiplied together are going to give me 18, and when added together give me negative 9. So
If 3 and 6 don't work, I mean, they jump out, but I don't think they work because if you use two negatives, you're going to get a positive 18.
yeah, that's right. Yep, and that's the problem. So I can go 3 times 6 is 18, but if I add those together, I'm just going to get positive 3. And if I do 3 times negative 6, Sorry, that'll give me negative 18. That will also give me negative 18, but when I add 3 and negative 6 together, I get negative 3. So no matter which one of these I use, I can't get the negative 9. So it's not easily factorable. So because it's not easily factorable, they want you to use another strategy to solve for the x values. Now, I could use the quadratic formula really easily and go, this is my a value, this is my b value, and this is my c value, and put that into the quadratic formula, and I get my x values. But they're saying don't use that, use completing the square. So when you complete the square, the first thing you need to do is bring the c value over to the other side. And I think sometimes students forget to do that first when they're completing the square. So I'm going to bring that c value over, and to do that I have to use algebra. If I have minus 6, to get rid of it I'm going to add 6 to both sides. That gets rid of the negative 6 on the left side and gives me positive 6 on that side. And so what I have here is I have a binomial. So I've gone from my trinomial down to a binomial. And now what I want to do is add b divided by 2 all squared to both sides. And my b value in this case is going to be this negative 9 right here. So I'm going to do that on the side. I'm going to take negative 9 and I'm going to divide by 2, and that's going to give me all squared. And negative 9 divided by 2 is going to is a fraction, which is probably the difficulty with this one is that you don't get a whole number. With this you're going to get 4.5, but that's okay. But I'm going to just keep it as a fraction. So I'm just going to leave it as, well actually I'm going to do first of all I'm going to square both the top and the bottom. So 9 squared is going to give me negative 81 on the top, and 2 squared on the bottom is going to give me 4. So what I'm adding to both sides is negative 81 over 4. Minus...
So isn't 9 squared 81?
Oh, sorry, positive 81, you're right. Because it's this, right? Thank you. So when I square it, I get rid of negative 9 times negative 9 would be positive 81. And then what I have to do to this other side is I have to add 81 over 4 like that. And I want to, first of all, simplify this side, which means that I have to take my 6 and make it into an equivalent fraction where I'll have 4 on the bottom. So 4 times 6 is 24. So 6, change that into a fraction that has a denominator of 4, becomes 24 over 4, because 24 divided by 4 is 6. So that's all I've done here. And then I'm going to add 81 over 4. So I'm just simplifying the right side. It gets a little bit messy, but it's workable. That's going to give me 105 all over 4. And that doesn't reduce into a whole number, but I might be able to... No, I think that's as far as I can go with that. Nope, that's as far as I can go. So now what I need to do is simplify my left-hand side. So 3x squared minus 9x plus 81 over 4. I should be able to factor that out now.
See, this is where I ran into the problem, right?
Yes.
I could not factor that.
I
mean, I could, but all you can do is pull out a 3.
Yeah, which I think would be helpful. It's just, how do I pull it out from the 81 over 4?
It becomes 27 over What's it become? It becomes, yeah, it becomes 27 over 4.
Plus 27 over 4, because 81 divided by 3 is 27 over 4. Okay.
And this is where I got stuck, right here.
Okay. So, and I might get stuck as well. And then we could then we would want to see if we could factor out x squared minus 3x plus 27, right, over 4.
It's not possible.
It's not working. Andrew, I don't know myself. Can we file this? I'll figure it out and then I'll get back to everyone on that.
Not a problem,
Okay,
because
perfect.
like
Because I'm not sure myself.
Yeah, from my understanding of completing the square, at least from the couple of videos that I watched, is they didn't touch on this like this eventuality if this happens.
No, my thing is this right here, and I forget how to do that if you have an a that's bigger than 1. So in what we've been working on is having a coefficient of 1 for our a value and then being able to go from there. But when your coefficient is larger than 1, what happens? And I can't remember, so I'm going to write down that one and do it after our Skype, and then I will post a video on that. There we go.
That would be great.
No problem. And this is completing the square. Okay. So we will shelf this one and put a pin in it. What's your next one? Do you have another one for me? I like that one because it's different from what we've done in the past. So as I said, I would have used the quadratic formula on this because of this a value being bigger than 1. But as the question wants you to figure it out using the completing the square, I'll find that out for us.
At least I hope that it wanted you to use completing the square, because that's how I was trying to do it. Maybe I didn't read the question properly.
No, I will see. I'll see what I can find. No worries. So do you have another one that you wanted to look at?
No, that was it.
Oh, that was it. Okay.
I had that other question, but that was one that another student had wondered about too. So, I mean, I still have about 10 questions to go before my homework is finished, so I might end up emailing you one.
Yeah, for sure. Do that. That would be great. But it's good because we kind of touched on a lot of things. We touched on just, the idea that the quadratics graph to a parabola, that not all parabolas have x-intercepts, and that section 1.4 and 1.5 is really looking at how to find those x-intercepts. And then you gave me one that we couldn't do, so that's great because then I can go and research that and then come back with an answer for that. When you get into 1.5, you get into some unexpected equations and how to solve the x values for that, because, so for instance, we're not in 1.5, we're looking at equations other than quadratic. So we're looking at absolute value, and absolute value graphs almost like a parabola, except that it's a V shape. So it's going to have x-intercepts as well, and you're going to see how to find those zeros. But we're also looking at graphing polynomials in third degrees and fourth degrees, which are going to give you these kind of wave functions, and you're going to get more than one x value for these ones, and it's looking at how do you factor polynomials like in third degrees and fourth degrees and still finding your x-intercepts that way. So you're going to have more than 2 solutions. You could have 3, 4, 5, that sort of thing. So just as a preview of what you're going to see in 1.5 is just how do you factor equations that are similar to quadratics, but you're looking at like third order and fourth order polynomials, and then this idea that absolute value functions are going to graph a V, and so how do you get the x-intercepts for that as well. Do you want me to show you just how to do the absolute values really quickly as a preview? They're easy because they don't have an x squared value. Do you want me to show you, Andrew?
Sure, why
Just because
not? We're here.
we've got 9 minutes, so this is a good one to come to look at. And it's at the very end of 1.5. So you'll get an absolute value equation like this, 5, and then you have an absolute value bar. This, that one's from the video. Let me see if I can find another example that's not from the video. Why bore you with one that we've already looked at? Oh, it'd be help if I'm in the right section. Here we go. Oh, there we go. Here's a different one. So here's the equation for the absolute value, and it is going to graph that V instead of a horseshoe. And you can see that our X variable is order of 1, so it's not a quadratic, and we do have our absolute value bars. So what we're looking for in this case is where the is going to be looking for the x-intercept. So where does the V pass through the x-axis? So when you're finding your x-intercepts, the first thing you want to do is you want to isolate just the expression within the absolute value bars. So you want to take anything that's extraneous over to the other side. So I want to bring the -20 over to the other side and the 4, and just leave the absolute value bars on the left-hand side. So to do that, I'm going to get rid of the -20 and bring it over, and you just do it algebraically. If I'm subtracting 20, then adding 20 to both sides, that will get rid of that there. And I'll get +20 on this side, and that brings this side, my left side, down to 1 for absolute value of 1 minus 2x. And then I want to bring the 4 over to the other side, and the 4 is actually multiplying. The operation isn't shown here, but it's like that. So if I'm multiplying the absolute value expression by 4, then dividing by 4 will get rid of it. And that's going to leave me with 1 minus 2x is equal to 5. And then to go, this is your last step. Once you get it down to where you have the absolute value of 1 minus 2x is equal to 5, to find your x values, what you want to do is take the expression of 1 minus 2x, and remember your absolute value, when you take away your bars, is either going to be your +5 or it's going to be -5. So removing the absolute value bars means that you are going to make it equivalent to the positive of that value and the negative. And then you just go ahead and solve for x. So I'm going to subtract 1 from both sides. That gets rid of that. That gives me -2x is equal to +4, and x is equal to -2, because 4 divided by -2 is -2. And then on my other side here, I get, I'm going to subtract 1 from each side. So I get -2x is equal to -6, and then divide by -2 on both sides, and I get x is equal to +3. And so my that means that my v is going to go through -2 and +3. So I'm going to get a v that is going to go something like this as my absolute value graph for this. So when you're trying to solve for your x's, it's just setting up your equation so that you isolate the absolute value bars to one side, and then it's trying to get to this part first. That's your first goal, isolating your absolute value expression, and then setting it to the positive and negative of whatever this number is. Now, the only caveat is this: if you get something that looks like this before you even move on, remember that absolute values can never equal a negative number. So if you get this where it's a negative number, that's going to tell you that that there are no solutions, that you're going to have that floating v either above or below the x-axis, and that's going to be the indicator that you have an imaginary x-intercept, as if your absolute, before you even solve for x, your absolute value bars equals the negative, then that can't be done. So that's just a heads up that that's going to give you the indication that you have that floating v, that without any x-intercepts. So that's what's to come, Andrew. But that one's not hard. Those are, I think the absolute value ones are fairly easy once you do a couple.
No, it makes sense to me. It's just to remove the absolute value bars so you can continue on algebraically.
Yeah.
And then, like you say, you do, if you remove them, you have to make the other side to an absolute value.
Yes, exactly. And know that absolute values, once you remove the bars, you're either going to get a positive or a negative number. You just can't have it start out this way, because we know that the absolute value always has to be a positive number. And that this one here does not make sense because we're saying that it's going to be negative. So, which is very different from what we're saying down here. We remove the absolute value bars, and as soon as you remove the absolute value bars, then you can have it equal to a negative number. But if the absolute value bars are there, then it absolutely can't equal a negative number, and you're going to get an imaginary x-intercept.
Is it possible to create an answer for that, like with the quadratics?
Oh, like to do your I values?
Yeah.
No. This is
No.
as far
So
as
it'd
it
just
would
be
come.
like no solution?
No solution. Yeah,
Gotcha.
that's it. Well, I think that's a great place to stop, Andrew, because it's looking at, we've looked a little bit at 1.5. Now, there's a bunch of different types of equations that you're going to be looking at, and if you find that you get hung up on one, then just send me an email on that, and I'm going to go and research that completing the square one and see what I can find for us to solve for that one. That must be a Practice Plus problem.
I'm going to go back and make sure that I didn't misread the question.
Okay.
because maybe it said use the quadratic function, and I thought that it was completing the square for some reason. You never know. I've been known to make worse mistakes than that. So.
Okay, no worries. If you find it, just hit the Ask My Instructor, and that will send me the link to it, or let me know if it said solved by a quadratic formula. But if not, I'll see. It has to be solvable, and I'll look up how to do that for us.
I'm going to go right into my homework here right away anyway, so I'll send you the link either way, just so you can have it handy for yourself.
Okay, great. Thanks, Andrew, and thanks for coming out tonight.
Yeah, no problem. See you next time.
Okay, see you next time. Bye.
Bye-bye.